Okay, so everyone's homeworks are going to be similar. The numbers themselves might be a little bit different, but it's the same sort of spirit of the question for everybody. So question number 14 in chapter 5. Now, remember the way this works is that if you click this, it shows you all the questions that I assigned to you in section 5.1. So I assigned 22 questions. But then if we go to the book, this right here tells you which question it is in the book. So the 14th question I assigned to you in this assignment turns out to be the 31st question in chapter 1, section 1. So if you go to your book and you flip to section 5.1 and look at the exercises, question number 31 is going to be this one. Of course, the numbers change just a little bit from person to person, but it's the same style of question, the same spirit of the question. Okay, so keep that in mind if you ever ask me to do a homework question. Usually people go by this, the question number in our assignment, but also some people like to go by this, which is the question number in the section. Or if it's a question that I did not assign to you, it's just a question in the book, then you can still refer to this for us to find it together. Anyway, this is the question you had a question about?
Yes.
Okay. So in a certain game of chance, a wheel consists of 38 slots numbered 0, 0, 0, 1, 2, 3, 4, okay, to 36. Okay, so 1 to 36 is 36, and then 37 and 38 with the 0 and the double 0. This is starting to sound a lot like the game of roulette, right? In casino, giant roulette, you flip it and a little ball dances around until it lands somewhere. Good. To play the game, the metal ball is spun around the wheel and is allowed to fall into one of the numbered slots. Complete parts A through C. Determine the sample space. Choose the correct answer below. Okay, the sample space is a list of all possible outcomes, simple outcomes, right? So what can happen in this game? Are there any questions about the game? Everyone's aware of about the game of roulette, correct? It's, if you've ever seen any James Bond movie or anything like that, it's just a very ancient, very classic casino-style game, right? So we're all aware of it, right? Spin the giant wheel, it spins around, a little ball lands somewhere. So in one experiment, it's one go of the game. You spin it one time, little ball dances around, and it lands somewhere. Right? If you know the game, then you know that it's impossible for it to land in more than one number, right? And it's impossible for it to land in no numbers. It's got to land somewhere. That's the way it was designed, right? Something bad would happen if it doesn't land on a number, right? If somehow it gets stuck somewhere, right? It wouldn't be, something would go wrong, right? The game's not designed to do that. Is that clear? Does anybody have any questions about the game of roulette? Good? Okay, so the sample space is simply for you to list down a list of all the possible outcomes that can happen when one turn of the game. So either the little metal ball lands on 00, or the little ball lands on 0, or the little ball lands on 1 or 2, right? These little dots here indicate that a pattern has been established. Let me zoom in on that a little bit. These little dots indicate that a pattern has been established and that we want to go all the way out through up to the number 36, right? So this has to be the correct answer. Number A is wrong because it's missing the other options of 0 and 00, right? Those are marked little indicators in the roulette, 0 and 00. Good. And these two are wrong because these are saying that these are the only options, that the ball could only land on 00 or 0. And this one is saying that the game is rigged so that it only lands on 00. Okay, is it clear why option B has to be the answer to part A? What is the sample space? We're good? Okay, so let's check answer. Fantastic, well done. Part B. Part B says, determine the probability that the metal ball falls into the slot marked number 3. Interpret this probability. Okay, so I put money down that the little ball is going to land on number 3. Okay, so assuming that this is a fair game, all of the options are equally likely of occurring. This is an example of classical probability, right? So all we have to do is count the number of ways that an event can occur divided by the number of outcomes in our sample space. Well, it literally told us how many outcomes there are in our sample space. It said that there are 38 slots. Of the 38 slots, of all the 38 different possible options when you play the game, only one of them is marked with a number 3. So therefore, there is 1 out of 38 number of ways for us to win this game. Good. Now it says round to 4 decimal places is needed, so let's get our trusty calculator out and divide 1 divided by 38. Clear that. 1 divided by 38. There. So this is the decimal result, and it says to leave it as a decimal. It doesn't say to write it as a percentage. So there's our answer, and it says round to 4 decimal places as needed. Okay, so that's going to be 1, 2, 3, 4. The 3 is in the 4th spot. So now we got to peek over to the 5th spot. And if the 5th spot is either a 0, a 1, a 2, a 3, or a 4, then we leave this alone. If the next one is a 5, 6, 7, 8, or 9, then we bump this up by 1. But in this case, it's a 1, so we leave it alone. So it's 0, 2, 63. 0, 2, 63. Good. Come back over here. Okay. Now, if this was a percent, we move this over, 1, 2, and it would be 2.63% chance that this can happen. Good. Okay, so that's going to be part A, because I know next it says interpret the probability. So the probability that the metal ball falls into the numbered slot marked with a 3 is 0.0263. So now check answer. Well done, fantastic. And now it wants us to do like a little explanation of what that means. What does it mean to have a 2.63% chance that something can happen? Okay, so one way to explain what a 2% chance means, right? Percent, right? Cent comes from the word, the word that means 100, right? Like a century, centipede, right? Cent, percent. Per 100, per 100. So even though there are not 100 little slots here, what we do is come up with a way of expressing the idea in terms of 100 so that it's easy to consider the concept. For example, even something like flipping a coin, there's only 2 options, heads or tails. But the probability of getting a heads, we turn it into a percent, 50%. So if there was 100 of them, 100 options, 50 of them would be heads, would be one way of saying percent, per 100. Sort of, maybe. So, okay, now cent is not a standard thing. We can change it into any, we can describe it in any way. And a classic way of doing it would be to move this up to either 1,000 or 10,000 to express it, to express our idea. Okay, so if the wheel is spun 1,000 times, it is expected that, well, exactly, and then this one says about, right? They're both identical in every word of the sentence, except this one says exactly and this one says about. Right, of those times to result in the ball not landing. Oh, this one says not landing in 3, whereas this one says landing in 3. So B is our answer. If the wheel is spun 1,000 times, it is expected that about 2.63% of those times, or about 26.3. Oops. If we multiply 2.63 times 1,000, we get this. But we want to do about, right? We want to round to the nearest whole number. So let me show you how I got that. So if we multiply this times, and remember a shortcut is to use this little ants button. So if you hit second and then ants, it'll do the previous result, right? Previous answer. Okay. We multiply that times 1,000, and we get this. So 2.631% of 1,000 is about 26.31, and this says round to the nearest whole number, so we're just going to put about 26. Okay, so one way to express what does it mean for something to have a 2.63% chance of occurring, we could say, if the wheel is spun 1,000 times, it is expected that about 26 of those times result in the ball landing in the slot number 3. So statistically, I expect that if I sit down in front of this game and play it 1,000 times and I keep betting on 3 every time, it's my lucky number, that's all I do, bet on 3, bet on 3, bet on 3, bet on 3, I expect statistically that I will win about 26 out of 1,000 times, and I will lose the rest of the time. Good. 974 times I will lose statistically. And this isn't about, because this is an exact situation. I'm not guaranteed that this is going to happen. This is just statistically what I expect should happen. And given the law of large numbers, right, I expect my empirical probabilities to approach the theoretical probabilities as we repeat the number of experiments a large number of times. And 1,000 is kind of a high number. Good. So if maybe I got 27, 28, 29, 30, 35, something like that, I would say that's fairly close. But I would be very, very, very surprised if I got a number that was much higher than 26 or much lower. If I played the game 1,000 times and I only won 1 time, then I would suspect something is weird. Right? This is starting to violate the rules of statistics. Either I'm incredibly unlucky, or maybe the machine is not fair. Maybe something is wrong with it. Okay? Any questions about this answer?
I have a question.
Yeah.
So when I completed the homework, I noticed that there was a trend about it saying it is expected that about, it was never exactly.
Correct.
Is there a time that it can be exactly? I know we're only approximating and can't really get narrowed down to that answer, but I wanted to know, would there be a time where it could be exact?
The times when we use the word exactly is when we know the theoretical probability and we know exactly what it is. So it's exactly that probability. Also, when we know something is for certain, 100% chance or 0% chance, that's when we like to use the word exactly. The reason we have to throw in the about here is because in order to explain what this, see, this is the, if we go out to all the decimal places here, I know we rounded, or really if we just express it as a 1 over 38. 1 over 38 is how we got this decimal, right? 1 over 38 is the exact probability. So if this was a sentence about the exact the probability, I would say, based on classical probability, I know the exact probability is 1 out of 38. Okay, but in order to explain what that means, what's the probability of 1 out of 38? What's the probability of 2.63%? We've introduced empirical probability. Empirical probability means that we just run the experiment over and over and over and over and over. And as we saw before with that baby experiment thing, as we repeat it more and more and more and more, eventually our empirical probabilities will get infinitely close to the theoretical probabilities, right? So that's why empirical is a good way to approximate a probability, but it's never we're never confident enough to say that it's 100% totally correct. We're just confident that it's close, fairly close, right? And so it's, in that sense, it's a little inferior to the classical probability that gives you the exact answer. However, in many, many situations, we won't really be able to do anything to find the exact probability. All we can do is use empirical techniques, experimental techniques, just repeat it over and over, and get a sense of what the answer is from that. So that's why we use the word about here, right? So the empirical results should be pretty close to that one, meaning that if we repeat the experiment 1,000 times, we should get about 26, right? And there's nothing special about 1,000. It's just an arbitrary number. I could say 10,000 times. That's another way of expressing this. If I repeat the experiment 10,000 times, I expect about 263 times I will win, right? All I did is multiply this decimal times 10,000, and that's how I get that. And again, we throw in that about because we know that in experimental probability, otherwise known as empirical, experimental and empirical mean the same thing. In those probabilities, they're never going to give you the exact answer, right? It's the most common way that we really work with probabilities because it's actually pretty rare that we run into a case where we know the exact answer. It's election season. So if we want to know how people will vote on anything, how do we know? There's 230 million people. It's hard to get a sense of how the people will vote on any particular issue. All we can do is maybe take a survey, right? And the survey is exactly empirical probability. We're randomly asking people, randomly stopping somebody and saying, hey, how are you going to vote? Right? And then that's one time. If we just base it off 10 people, that's not a really good survey, right? We just randomly pick 10 people and somehow we're going to make a guess about how 320 million people feel based on 10. That's not a good way to do it, right? So we want a bigger sample. Okay, let's randomly ask 1,000 people. Okay, that's a little better. But still, there's 320 million people and you want to base it off just what 1,000 people feel. Okay, so maybe ask 2,000. 5,000, 10,000, right? So the more people you ask, the more confident you are that your little experimental results, your empirical probabilities, will approach the real answer, right? That real probability, that real result that no one really knows until the votes are cast and everyone's vote is actually counted. Then we'll know the real answer. Did that answer your question?
Yes, it did. Thank you.
Good. Okay, any more questions on this one? Let's check answer. Is that the last part of it? Excellent. Okay, one last part. Determine the probability that the metaball lands in an odd slot. Okay, an odd slot. So we have 0, 0, 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? All of those guys. So let's write them down. Whoa, come on. What is this? Go away. Delete this thing, go away. Let's go over here. Okay, so we have the numbers 0, 0, 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Okay, I think it stopped at 36, right? Okay, so now where are all the odd ones? Well, odd, 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 right? And then the way I wrote it would be all the ones right below it. So all of those guys, all of those guys, all of those guys. These are all the odd ones. So if I walked up to this roulette table and I put $100 that the next ball will land on an odd number, I would be a winner if the ball lands in any one of these values, right? Oops. So there's 4 of them there. There's 4 of them there. There's 4 of them there. There's 3 of them there. And there's 3 of them there. So 4 plus 4 is 8, 12, 15, 18. There are 18 ways to win. Okay, so now remember our style of notation. Probability that the little ball is equal to an odd is equal to the number of ways in which the little ball can equal an odd divided by the number of values in our sample space. Right? Okay, so we just counted them. There are 18 ways in which the little ball can be an odd, result in an odd, divided by the number of outcomes in our sample space, which we said were 38. Okay, so now we just divide 18 divided by 38, and that'll be our answer.
I got 0.47368.
Okay, sounds good. 18 divided by 38. 463. Okay, and it says round to 4 decimal places, so we got to go 1, 2, 3, 4 right here, and then peek over. There's an 8, so we got to bring this up to a 7. So 4737 will be what we round this to. 0.40. Wait, what is it? 4737. 37. 4737. Okay. Okay, so then check answer. Good job. And then again, that little interpretation thing. How do we explain to someone what that means, right? If someone is hasn't taken this stats class and wants you to explain to them, what does it mean for something to have a 47% chance? 47% chance. Okay, well, this would be kind of like an explanation. Think of it this way. If you repeat the game 100 times, right, it's just an arbitrary choice. Notice up here they said 1,000. Here we're saying 100. Okay, if we repeat the game 100 times, statistically, I would expect that about, right, not exactly, but about 47 times. Because if you multiply this decimal times 100, you get 47.37. So approximately about 47 of those times, you expect the ball to land on an odd number. Good. Check answer. Good, 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 good. And also notice that people normally think of evens and odds as being about equal. So the odds of being even, the odds of being odd, you're like, okay, about the same. And in most cases they are. But in this case, it's not 50%, it's 47% instead of 50%. Why is that? That's how the casino makes money. The casino introduced the 0 and the double 0 to tilt the odds in their favor. That's how they cheat. I don't know, it's not really cheating because they set up the rules, so that's how they set up the rules to win. Right? The system is rigged. They're going to win. Good. Questions, 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 questions? No, no, no? Okay, so keep chipping away at 5.1 then. I think that's, oh yeah, similar questions. That's it. So keep chipping away at chapter 5.1, 5.2. You should be able to complete up through 5.3 by now. And we're going to move on to chapter 5, section 4 today. And unfortunately, this is where it actually starts to get confusing. Delete this. Okay, chapter 5, section 4. Conditional probabilities and the general multiplication rule. Okay, so far we worked with the addition rule, right? We know that if two events are disjoint, we know how to add them. If two events are not disjoint, we know how to add them. We know we have to take the more general addition rule. That was back in section 5.2. And then in section 5.3, we thought about the multiplication rule. and that's when we use the and statement, right? The and statement means that we can multiply them, right? And here, let me write that down. So in 5.3, in the previous section, we learned that if events A and B are independent, then we know that the probability that event A and event B happens is equal to the multiplication of event A times the multiplication times the probability of event B. Good. So that was in the previous section. So we talked about what independence means. Right? Two events are independent if the occurrence of one does not impact the other. In some cases, it's really obvious that one event will not impact the other. The probability that you get struck by lightning, the probability that I will buy a Tesla this year, right? What the forces involved with me buying a Tesla and the forces of nature involved with you getting struck by lightning have nothing to do with each other, right? So they're independent events, obviously. So we figure out the probability that I will buy a Tesla this year, and we figure out the probability that you will get struck by lightning, and the probability that both events will happen, right? This end statement means that both will happen. The probability that they both happen is equal to the multiplication of the two. Good. Probability that you win the lottery this year, the probability that you die on a plane accident this year, they have nothing to do with each other, right? The forces involved with you dying in a terrible plane accident have nothing to do with the forces involved with you winning the lottery. And so the probability that they both happen is going to be equal to this multiplication. Find them separately and then multiply them together. Good? Good. So I think that's kind of intuitive. If you have a rare thing happening and then another rare thing happening and the probability that they both happen at the same time, well, we multiply them. And remember that with numbers, again, this is another kind of curiosity of numbers that's really interesting. I covered this before, I mentioned this before, that if we have the number line here, 2, 3, 4, right? Whenever we're dealing with numbers that are strictly bigger than 1, whenever we grab two numbers, some number there and some number there, b, whenever we grab two numbers and we multiply them, the multiplication is going to be even bigger, right? Bigger. Good. But when we grab two decimal numbers, somewhere between 0 and 1, whenever we grab two of these, right, any numbers here and any numbers here, for example, a and b, and we multiply them, their multiplication is going to be even smaller, but still within 0. It's not going to go into negatives, but it's going to be smaller. Good. So if we have a rare event, we have some probability of event A happening, and then let's say it's a rare event, like getting struck by lightning or winning the lottery or some event. And then we have another rare event, a really rare event. How about what's the probability that in the year 2030, I will be governor of California? Who knows? I might run. 10 years from now, who knows, right? But the odds are small, very, very, very small, that I would run or that I would win. So we know that's a rare event. Okay, what's another rare event? What's the probability that the Los Angeles Rams will win the Super Bowl in the year 2030? Again, 10 years from now, who knows, right? Who knows what players will be on the team, what coaches, who knows if they even are still in Los Angeles, right? They obviously have no loyalties, so who knows? They left their previous city, maybe they leave us too, right? Any rate, so who knows what's going to happen then? But if we can figure out the probability of one, and we can figure out the probability of the other, the probability that they both happen at the same time is going to be the multiplication of the two, right? Because they're obviously independent. The forces involved with the Rams winning the Super Bowl in the year 2030 and the forces involved with me becoming governor of California in the year 2030 have nothing to do with each other. They're clearly independent, so we multiply them. Good? Okay, that was the previous section. Now we're going to deal with cases where they are not independent. They are dependent. There's some sort of association between the two events. The probability that I become a billionaire by the year, well, let's not even get that extreme. The probability that I am a multi-millionaire by the year 2030, whatever that is, right? It might be a small chance, but whatever, it doesn't matter. The probability that I become a multi-millionaire by the year 2030, and the probability that I, become governor of California, now they're kind of connected, right? If I am a multi-millionaire, there is a slightly better chance that I can become a governor, right? If I told you I'm running for governor right now, you're like, whatever, you're just some guy. But if you knew that I was worth $300 million, you'd probably take me more seriously. Like, oh, okay, this guy's got some money. Maybe he can get in this game, right? I got connections, I have access, I have money. Money buys you access and influence. So the odds that that I actually become a governor, or at least run for governor, become a little bit more likely, right? Everyone has their own sense of whether it's a big increase or a small increase, so we're not judging how much more likely, but it clearly has some sort of an impact, right? Kanye West is apparently running for president. And if he was just some random guy off the street, some random guy off the street told me that he wants to run for president, okay, that's incredibly silly. But just the fact that he has money buys him influence. He's going to spend some money, and that means that he at least has some opportunity of being elected. He's going to be on the ballot in some places. He's going to get commercials up on TV in some places. The odds aren't zero. Hopefully they're really, really small, but it doesn't mean they're zero. Good? So one is connected to the other. Money is connected to possibility of winning elections, right? Whenever a billionaire kind of tosses around the idea that they might run for office, we take them seriously because they have money. Like, yeah, this guy might actually run. This guy might actually I shouldn't say a guy, this person, male or female, might actually make a run for it because they have the money. Good? Okay, so we're looking at cases where one force does impact the other. The one event might influence the other. So we're going to learn how to compute conditional probabilities, and then we're going to compute probabilities using the general multiplication rule, right, as opposed to this one, which is the multiplication rule for the cases when events A and B are independent. Okay, so let's get on to the definition then. So the notation we're going to adopt is to use this slash like this. So this is the probability that event F happens given event E has occurred, right? So this reads the probability event F given event E. It's the faster way of noting this, right? So it is the probability event F occurs given that event E has occurred. Good, good. Sort of, kind of, maybe. Let's jump into an example. Okay, so suppose that a 6-sided die is rolled. What is the probability that the die comes up as 4? Right, this is the hottest game in Vegas. Roll one 6-sided die. Right, so here's our experiment. Roll one 6-sided die. And in all of these, by default, we assume they're fair unless they specifically tells us they're not, right? Otherwise, I'd always have to write, assume it's a fair die, assume it's a fair coin, assume it's a fair, right? So we always assume everything is fair unless they specifically tell us it's not. So it's one 6-sided die. We're going to roll it one time. So this is one execution of the experiment. And event E is going to be equal that it comes up 4. The die is a 4. Good? Okay, so we know how to do this thing. The probability that event E happens is equal to the number of ways then event E can happen, divided by the number of values in our sample space. Good. So the number of ways that a 4 can come up, there's only one way. Roll a 4. Very easy. And how many possible outcomes are there? Well, there are 6. Right? So it's 1 out of 6, which turns into 0.16666, so we can round it to 67. Good. Or approximately 16.67%. Good. Okay, now suppose that the die is rolled a second time, but we are told that the outcome will be even, right? We know for sure that even will happen. Good. So this is what we're going to do. What's the probability that it comes up a 4? What's the probability that the die equals a 4 given that we know for sure that it's going to be even? Okay, we're guaranteed, right? So like maybe this is the hottest game in Vegas. You roll a die and you're just going to bet that it's the number 4. So you're going to go down there and you put $100 on 4. You have a 16.67% chance of winning. Okay? But let's say that maybe your friend, you got a friend who's a dealer there, and you guys are going to kind of do something special and try and win a little money from the casino. So maybe you guys put a trick die in there. It's a trick die. The way it was made, the balancing, like the numbers are all on there. Obviously, you got to be able to look at it and think that it's a normal die. But maybe the way that it's made, the internal weight of it is made in such a way that it only lands on even numbers. It's a trick die, right? So we're going to cheat the system. So I already know it's definitely going to be even, right? So if I go in there and I put money down on 4, it's no longer going to be the same probability, right? Because I know for sure it can't be a 1. It's going to be an even number. We've tricked it. We know for sure it's even. Or maybe it's a 2, or maybe it's a 4. So now, if I put money on the fact that it's 4, there's still only one way that I could win, right? It's the number of ways. Well, let's skip the notation for a second because we're gonna think about that notation a little bit more in a second. But there's only one way to win, right? Still, it's a 4. However, the denominator now changes because there isn't 6 possible outcomes. Since it's even, since I've put in a trick die, I know for sure it could only be a 2, a 4, or a 6. So this turns into 1/3, right? So my odds are really 0.3333, which turns into 33.33%. Right? Instead of having a 16% chance of winning, now I have a 33% chance of winning. Putting in this trick die here has increased my odds of winning. Does that make sense? Any questions, any questions, any questions? So, knowing that this happens affects this thing. Right? Originally, that was the probability that we roll a 4, right? And event E was die equals to 4. So I really should have, introduced this E thing and just made it a little easier. So let me just put it this way. This is die equals 4, die equals 4, die equals 4. Okay, so the probability that die equals 4, we had 16%. The probability that die equals 4, given that it's even, now that jumps to 33%. So that means that this event changed the probability, right? This information changed that probability. That means that these two events are not independent. These two events are dependent, right? They're connected somehow, right? So that's another thing we can conclude from this. Thus, event die equals 4 and event die is even are dependent, are not independent, or dependent. Any questions? Good. Questions? No? Okay, moving on then. Okay, so this is what the author did, same thing. Here's our sample space of the original roll, 1, 2, 3, 4, 5, 6. So the probability that we roll a 4 is 1 out of 6. That's the 16.67%. And the probability that we roll a 4, given that we know is definitely even, has narrowed down our sample space down to a smaller subset of just a 2, a 4, or a 6, of which the probability of getting a 4 is going to be 1 out of 3. Good. Okay, so here is the notation that we want to adopt and a formula for it. So if E and F are any two events, then the probability of F given E is equal to the probability of E and F divided by the probability of E, which is equivalent to the number of ways of getting E and F divided by the number of outcomes in event E. Good. So the number of outcomes in events E and F divided by the number of outcomes in E. The probability of event F occurring, given the occurrence of event E, is found by dividing the probability of E and F by the probability of E, or by dividing the number of outcomes E and F by the number of outcomes in E. Okay, so I know this is looking kind of confusing at this point. So let's go to one of our classic examples with little ping pong balls, and we will go through a little summary of all the probabilities we have in our pocket already, and we'll come back and revisit this right here, and hopefully it'll make more sense. So right now, this is probably gibberish, and that's okay. So let's do an example, and I'm going to need more space. Let me go to another sheet. Let's go back to our classic game of a little ping pong ball with numbers on them. So here's our sample space. Right? Remember, this is the experiment where one little ball is selected, and the numbers are from, let's just say from 1 through 10. So experiment is going to be to select one little ball. Select one ball from balls numbered from 1 through 10. I should probably establish a couple there before the number. Okay, from 1 through 10. Good? Okay, so now I'm going to have a couple of events out here. Here is event E. And let's say this is event, W. There's nothing special about the letters E and F. They just kind of happen to be used often. But it could be any capital letter could be used to represent an event. Okay, so let's say that I'm event E. I'm going to put some money down that the little ping pong ball is going to be the number 1, or the number 2, or the number 7, or the number 6. 1, 2, 6, 7, that's what I think is going to happen. Okay? My friend, on the other hand, thinks 7 might be the winner, or 7 or 6, so they're also wagering. That's why it's in this overlap situation here, because that means that those outcomes, both people are wagering on those outcomes. Okay, but also my friend thinks it might also be the number 10. Put some money on number 10. Good. Okay, so then the rest are options out here, outside those. So maybe the number 3 is out here. The number 4 is out here. The number 5 is out here. The number 6, 7, the number 8, and 9 are out here. Good. So that's 10 options. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 different options, right? So this is our sample space. It takes care of every possible outcome that can happen when one experiment is selected. One ping pong ball is selected. It could be the number 1, it could be the number 4, right? And I put money down that it's going to be one of. So far we're good with that setup. Okay, so now we can use this to set up various things we've learned so far. So let's identify our events. Event E is the numbers 1, 2, 7, 6 and 7, if you want to put them in order. 6 and 7. Event F is equal to the numbers 6, 7, and 10. Okay, remember, we're only doing this experiment one time. So let's find some probabilities. What is the probability that event E occurs? Well, notation-wise, this is the number of ways in which event E can happen divided by the number of ways in our number of options in our sample space. Good. So the number of ways that E can happen, that's 1, 2, 3, 4 ways. 4 out of 10. So my probability of winning is 40%. 0.40 if we divide those, which turns into 40% chance of winning. Good. Probability that event F will happen. Oops, see, I went back to my F. I'm used to F's. Well, no, let's leave that as a W. Event W. So event W is that. Okay, the probability that event W happens is equal to the number of ways in which event W can occur divided by the number of values in our sample space. And there are 3 ways in which W can occur out of 10, which turns into 0.30 or 30%. Good. Okay, so we have our probabilities, and I'm going to start writing them down up here just to get rid of all the mess. Probability of event E, we said, was 40%, 0.40. Probability of event W, that's equal to 0.30. Okay, what about the probability of both of them winning? Is it possible that in one experiment, one ball is selected and both E and W events happen, which means both of them are winners? Yeah, it could be one of these balls, right? If the dealer picks up the little ping pong ball with a 6, then we're both winners. Or the 7, then we're both winners. Good. So what's the probability of E and F? I'm sorry, E and W. I keep going back to F. So the probability that we have event E and event W is equal to the number of ways in which event E and W can happen at the same time, divided by the number of ways in our sample space. Good. That is going to end up being equal to 1, 2, right? That's how we can count them. We have the benefit of a nice Venn diagram to figure out all possible outcomes. And there are 2 ways in which E and W both happen at the same time. That's this little football-shaped region in the center that represents the overlap. Good. Okay, so there are 2 ways that event E and W can happen, divided by the number of values in our sample space. So that means that this is equal to 0.20 or 20%. Good. Good, good, good. Okay, so that means, let me come back up here and continue to put my little list together. E and W can occur in 20% of the ways, 0.20. Good. What about E or W? What's the difference between the two? E and W is saying both of them are winners, right? There's only 2 ways that can happen. On the other hand, if I want to find the probability of E or W, it means that either E wins or maybe W wins, or maybe they both win, right? One or the other. What's the probability of E or W? E or W. Okay, so let's write that down notation-wise. The probability that E or W happens, good. This is going to be equal to the number of ways. We have two ways to figure this out, so we'll do it both ways. One of them is to count things. Since we do have the benefit of a nice Venn diagram, we can just count things. E or W, the number of ways that E or W can happen, divided by the sample space. And the number of ways that E or W can happen by counting things, well, I can just count them. 1, 2, 3, 4. There's 5 different ways that E or W can happen. Okay, so that's 5 over 10. Good. And remember, let's put them down. The 5 is this, right? 1, 2, 3, 4, 5. This 5 is counting. This 5 is counting the 1, the 2, the 6, the 7, and the 10. Right? Everybody has bet on these numbers. Both people have bet on these numbers. Right? If these numbers come up, somebody wins, or maybe both win, but somebody's going to win if the dealer picks one of these numbers. Good. On the other hand, the only way that they can both win is if it's the number 6 or the number 7. That's the only way that both of them are winners. Any questions about that? The only way that they're both winners, or if they're both winners, that way. Okay, so if we convert this into a decimal, we get that this is 0.50, which equals to 50%. Good. Okay, now we did have another way of figuring out an OR statement. Sometimes we don't have the benefit of a Venn diagram. We have to rely on our formula. And the formula says that the probability of E or F is equal to the probability of E plus the probability of W. Did I say O, F again? Probability of E or W is equal to the probability of E plus the probability of W minus the probability of E and W. Right? That's the general formula. Add them together, but then you got to subtract away the AND statement. So the probability of E, we already figured it out right up here, is equal to 0.4. This is 0.40 plus probability of W. Probability of W is 30%. That's going to be 0.30 minus the probability of E and W. That's this one. We just calculated it. It's equal to 0.20, right? And so this equals to 70 minus 20 gives you 0.50, right? It matches with the results we got when we were able to just count. Any questions? Okay, so far this has just been a review of what we had already learned in the previous sections. And so, oh man, it's going to start doing the weird zooming thing. Probability of E or W, we said, is equal to 0.50. Okay, so it's just a review of the previous probability properties that we've already known. So now let's see what happens with this conditional probability. In order to kind of express the idea of what it means for it to be conditional probability, consider the following kind of scenario. So this is one experiment. We're going to pick one little ping pong ball, and if it's the numbers 1, 2, 6, or 7, event E has occurred. I put money down. I'm event E. I win money if those happen. My friend Wilson put money down on a 6, 7, or a 10. So if the dealer picks one of those little ping pong balls, then Wilson is the winner. And if it's a 6 or a 7, we're both winners. Okay? So let's say that I put my money down, Wilson puts his money down, and then we're waiting for the game to happen. Other people are putting their money down and stuff, but I'm in Vegas. I just put money down. I'm anxious. I need a drink, so I walk away. I go to the bar, get myself a drink. I'm strolling back to the table when I hear my friend Wilson yell out, "I won." Okay? So now I have new information. It's still the same experiment. It's only happened one time. When I originally put my money down, I had a 40% chance of being a winner, right? Probability that E happens is equal to 40%. But now I have new information. Now I know that W definitely occurred, okay? So that's conditional probability. So let's find the probability that E happens given that I definitely know W occurred, right? He yelled out, "I won," right? As I was strolling back to the table with my drink in hand, I heard him say, I won. Now, it would have been more useful if he yelled out the answer. He picked how does he win? He picked a 10. Woo! If he yelled out that the answer was 10, then I would know even more information because I know exactly what happened. But just him yelling out, "I won," I at least know it had to be one of these guys, right? Because that's how he's a winner. So given that he won, what happens to me, right? That's really what we care about, right? Ourselves. So yeah, you won. But how does that affect me? Okay, so what we're going to do is we're going to count. Because the fact that he won means that our sample space is no longer all 10 options. Our sample space is really just going to be the number of ways that W can occur, right? Because he won. And there's only 3 ways that can happen, right? The fact that he yelled out, "I won," means that it had to be either the 6 or the 7 or the 10. That's how he wins. 6, 7, or 10. That's how he's a winner. Right? Okay. So the only way that I could win now is if we both won. Right? There's no way for me to be the sole winner because he already won. So the only way that I can now win is if we're both winners. So now we have to count the number of ways in which both he and I are both winners. Right? And how many ways were there for both of us to be winners? There was 2, either the 6 or the 7, right? So there's 2 ways that can happen. That makes it a 2 out of 3, right? This 2 refers to the number of ways in which we can both be winners, and that's the 6 and the 7. If the dealer picks a 6 or a 7, we're both winners. That converts the probability into 2/3, which is 0.66667. Just round it to 4 decimal places like that. Or a 66.67% chance of winning. What just happened? When I originally put my money down, I only had a 40% chance of winning, right? The probability of E occurring, when I put my money down, I had a 40% chance of winning. But now, probability of E occurring, given that W has occurred, is now equal to 0.6667. It went up. So what can I conclude? Events E and W are dependent. They affect each other. This additional information helped me, right? It improved my probabilities of winning. Sometimes it improves them. Sometimes it doesn't improve them, right? Makes them lower. Doesn't matter. Somehow it impacted them. It affected them. Good. Questions? No? Okay, let's figure it out the other way around. Let's do the probability of W. Probability of W given that E has occurred. So let's flip it around the other way around. We both put our money down on this game, right? Initially, I had a 40% chance of being a winner, 4 out of 10. My friend had a 30% chance of being a winner, 3 out of 10. but then maybe he has to go to the bathroom or go get a drink or whatever. He just walked away. And as he's walking back to the table, he hears me yell out, "I won," right? So we definitely know that event E has occurred. So the probability that he wins, given that he definitely knows now that I won. Right? Remember, we're not doing a new experiment or anything. It's the same experiment. It's just that now we have more information. Before he walked away, he had a 30% chance of winning. But now that he has new information, how has that affected his chances of winning? That's what we want to know. Okay, so because we definitely know that I won, now the sample space reduces down to just the number of ways that E could win. Good. And there were 4 of those. There were 4 ways that I could be a winner. That's ugly. There were 4 ways that I could be a winner. Good. Coming up here. It could be one of those, right? He heard me yell out, "I won," so it's got to be one of those. And so now he has to think to himself, well, what are the chances that he wins? Well, if I won, the only way he could win is if we both won, right? Since I won, it couldn't have been the 10, right? So there's no way for him to be the winner and me be the loser once he heard me yell out, "I won." So now the division here is going to be of the number of ways in which E and W can occur. Good. E and W, which there are only 2 ways that can happen. Right? So again, this 2 is referring to the number of ways that we can both win, which is the 6 and the 7, whereas this 4 accounts for the ways in which I could have been a winner, which was the 1, the 2, the 6, and the 7. Good. Which then means it's 2 out of 4, or 50%, which means the odds he wins are now 50%. They've improved. He used to only have a 30% chance to be a winner, and now, given this new information, the odds have changed to 50%. So going back up here, we have the probability that W given E is equal to 0.50. Good. So notice, first of all, that the order matters. Right? So P of E given W is not going to be the same answer of P of W given E. So the order is important, and they mean different things, right? It's always given. This bar right here is read as given that this is true. So the probability of W given E, given that E has occurred, or given that E is true, changes. Good. Good. Okay, now back to notation. The probability that, say, let's go back to E given W. We said that this is equal to the number of ways in which E and W can occur, divided by the number of ways in which W can occur. So it's divided by the n number of ways that W can occur, because remember, this means given. Right? This is given. So if I walked away and I heard my friend Wilson yell out, "I won!" Right? I know W has occurred, so we divided by the number of ways in which W can be a winner, because I already know that W is the winner. Good. So now the only way that we can, I can be a winner is if we're both winners. Oh, sorry, this Zoom thing just kind of ruins everything. Okay, so now the only way that I can be a winner is if we're both winners, right? So that's how we can do it. And if we have a Venn diagram, we can just count things at this point, right? The number of ways that we can both be winners, that's 2, divided by the number of ways in which W can occur, that's 3. This is how we got the 2 out of 3. However, I'm going to do a little algebra trick here. What I'm going to do is I'm going to take this, E and W, divided by n of W. And what I'm going to do is I'm going to multiply the numerator and denominator by the same thing. And I'm going to multiply it by 1 over n of s, right? That fraction, like that, and then divide it by the exact same fraction, like that. Little algebraic trick. Good. This, whatever this is exactly the same as this, and we know from fractions that whenever we have a fraction where the numerator and denominator are identical, then they represent a 1. So I'm multiplying this fraction by a new version of 1. Okay? All right, so this then simplifies into, this will then simplify into n of e and w divided by n of s in the numerator. There'll be a giant fraction where the numerator is this fraction, and the denominator is going to be n of w divided by n of s. Right? All I did is I multiplied these two things together. Right? I can put a little 1 there. So multiplying these two things together gets me this one. And multiplying these two things together gets me this one. Good. So there's one giant fraction. Right? This is the giant fraction here. And now I have another fraction in the numerator and a fraction in the denominator. And if we look at this, this is the exact definition of the probability of E and W. Right? Forget conditional probability, going back to the probability of E and W, that's equal to the number of ways that E and W can occur divided by the number of values in our sample space. So this numerator is equal to the probability of E and W, right? And we can divide that by this, and this is exactly equal to the probability of W. Number of ways that W can occur divided by the number of values in our sample space. This is the probability of W. So we get this formula, the probability that E given W is equal to the probability of E and W divided by the probability of W. Good. We can confirm this just to make sure it's true. We already know that the probability of E given W was equal to 0.6667. Good. So the probability of E and W, we know that that one was equal to 0.20 from previous work, 0.20. And the probability of W was equal to 0.30. And if we divide those two things together, we're going to get 0.6667. The exact same answer as we got before. Good. So in some cases, we will have a nice Venn diagram where we can count things. But in some cases, we won't have that benefit. It will be a complicated word problem of some kind. And we might have to rely on this formula in order to find our answer. Good. Good, good. Questions, 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 questions. Also notice that this formula, come on. Also notice that this formula, P of E given W equals to P of E and W divided by P of W. This formula, what we could do is multiply both sides by P of W times P of W times P of W. These guys cancel. And then we end up with a new equation. Right? We end up with P of W times P of E given W equals to P of E and W. Good. So the multiplication of the probability of E given W times the probability of W is equal to the probability of E and W. Good. It's a good place to get back to our slides. Any questions about all of this? All right, let's get back to this thing then. And that's where this comes from, right? So that's where this definition comes from. Probability of f given E is equal to the probability of E and F divided by the probability of E, which is equivalent to the number of ways that E and F can occur divided by the number of ways that E can occur. Okay, let's move on to a different example. A survey was conducted by the Gallup organization, conducted May 8th through 11th in 2008, in which 1,700 adult Americans were asked, which of the following statements comes closest to your belief about God? You believe there is a God. Sorry, you don't believe there is a God. But you do believe in the universal spirit of some higher power, or you don't believe in either. The results of the survey by region of the country are given in the table below. Okay? So we asked, what are your thoughts about higher powers, right? So they were given 3 options. So in reality, people's answers are probably a lot more complicated, but we've restricted them down to one of these 3 options. Choose which of these sentences is closest to your own ideas, right? You believe in God, whatever God that is, right? Everyone has a different idea of what a God is and which God, but it doesn't matter. The question was just simply, do you believe in God? So you believe in God is one of the options. You believe in some sort of universal spirit, right? So maybe not a God as sort of normally defined, but some sort of universal spirit of some kind. Or maybe you believe in neither. Good. And the results of this survey, remember 1,017 people were surveyed, and we have ourselves this table that describes the results by regions of the country. So the East, the Midwest, the South, and the West. Good. So just to make sure we're all reading this table accurately, this is saying that 212 people were in the Midwest, and their answer was yes, they believe in God. Good. This is saying that 9 people were in the South, and they answered, I don't believe in either. Good. Questions, questions, questions? This thing is really behaving weird. Hope it doesn't crash. Anyway, so part A. What is the probability that a randomly selected adult American who lives in the East believes in God? Okay, so the fact that we said who lives in the East means that we are focusing our attention only on those that live in the East, right? So let's highlight this. So if we're just going to be focusing our attention on these people, oh, this thing is really unhappy right now. That was not pretty. Okay, so there's these people, and these people. And we're going to focus our attention on them, right? Because it says who live in the East. So we're only focusing on them. So instead of focusing on all, 1,017, we're only going to be focusing on the people that live in the East. And we want to know what's the probability that they believe in God. What is the probability that a randomly selected adult American who lives in the East believes in God? Okay, so this thing is very unhappy. So the probability that someone believes in God, believe in God. How many people believe in God in general, right? That's not the answer to this one yet, but I just want to answer this one. What's the probability they believe in God? Well, of the 1,017 people that were surveyed, how many people said, yes, I believe in God? Well, that would be the 204 plus the 212 plus the 219 plus the 151. Oh, sorry, 152. Right? Those people divided by the 1017 would give me the probability that one randomly selected person from this survey believes in God. So if we add 204 plus 212 plus 219 plus 152, I get 787 divided by 1017. You know what? Let me close down this thing, because maybe that'll help my computer. It seems to be having trouble. So let's quit that. No, it's one less program that it's running. Maybe that'll be helpful. And why do I have Chrome on? Okay, so let's end that program. It's one less program that needs to worry about. Okay, so 787. Now if I divide that by 1017, I get to 7738. .7738. Good. So there's a 77.38% chance that one randomly selected person believes in God. Okay, now this question, however, was asking us about. Okay, so let's continue. Let's find the probability that a randomly selected person lives in the East. How many people live in the East, right? So this is going to be equal to the number of ways in which we can find people that live in the East. Well, people that live in the East, that's going to be these people here. So the probability that they live in the East is going to be equal to 204 plus 36 plus 15 divided by 1017. Good. So 204 plus 36 plus 15 is equal to 255 out of 1017. So if we take that and we divide it by 1017, I get 2507. 0.2507. Good. Okay, finally we can get to this question. What's the probability that someone believes in God given that they live in the East? Good. Okay, so according to our rules, we can do this in a couple of ways. This turns into, one way to do this is the number of ways in which they believe in God and they live in the East divided by the number of ways in which someone can live in the East. Right, that's one of our formulas. So, how many people believe in God and live in the East? Right, so that's when we got to come up here and note that these people right here, they live in the East and they believe in God. 204 of them believe in God and they live in the East. Right? Now, because we're guaranteed it's going to be someone that lives in the East, it's going to be one of these people. Right? This sum right here is 255. Live in East. Good. Good. So this fraction then has to be 204 divided by 255. This fraction has to be 204 divided by 255. Good. Which we can turn into 204 divided by 255 equals to 80% chance. 0.80 or 80% chance. Questions, 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 questions? What if it was the other way around? What if they ask us, what's the probability that they live in the East given that they believe in God? Right? Order matters. What's the probability that they live in the East given that they believe in God? Good. So that's the number of ways in which they can both live in the East and believe in God, divided by the number of ways in which our outcome is someone that believes in God. Right? Since this is the given over here, given that one, then we're guaranteed to be only focusing on the people that believe in God. If we come over here, and hope this highlighter works this time, let's put them in blue. If we're only going to be focusing our attention on the people that believe in God, then that's these people. Right? These are all the ones that believe in God. Given that I'm focusing on just the people that believe in God, what's the probability that they live in the East? So that's going to be this number divided by the sum of all of these. Good. So what is the sum of all of those? If we add these up, the sum of all of these, so we get 204 plus 212 plus 219 plus 152, and that's where we get the, oh, we already had to believe in God. That's the 780, that's this guy, 787, that's 787, right, the sum of all of these. Good. Okay, so this is going to be equal to 204 ways in which people both live in the East and they believe in God, divided by 787 number of ways in which someone selected believes in God. So that would be 204 divided by 787 gets us to 2592. Zero 0.25992. Good. So definitely very different answers. The probability that they believe in God given that they live in the East, 80%. Probability that they live in the East given that they believe in God, there's only a 25% chance of that. 25.92%. Good. So the order definitely matters. Any questions? Good, good. Questions, 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 questions. What is the probability that when I said the American who believes in God lives in the East? Okay, we already answered that one. What about, let's look at another one. How about, what's the probability that that someone selected lives in the East? Oops. Probability that someone selected lives in the East given that they live in the West. Right? Even that sentence makes no sense. Right? How can they live in the East but they also given that they live in the West? That makes no sense. So, right, this is given. Okay, well, following our little notation style, this means it's the number of ways in which a person can live in the East and live in the West, divided by the number of people that live in the West. Okay? But the number of people that live in the East and the West, that's going to be 0. Right? Divided by the number of people that live in the West, well, okay, if I wanted to find that answer, it would be equal to 152 plus 76 plus 26. But 0 over anything is 0, so the answer is just going to be 0. Right? As long as the denominator is not 0, then 0 over any number other than 0 equals 0. And that makes sense. The probability that someone lives in the East given that they live in the West, that makes no sense. Any questions? Questions? No. Okay, so these are the same answers. Let's look at another example. Sometimes we won't have the benefit of a nice table. We just have a word problem we have to decipher, and then we have to rely on our formulas. So in 2005, 19.1% of all murder victims were between the ages of 20 to 24 years old. Also in the same year, 2005, 16.6% of all murder victims were between the ages of 20 to 24 years old and were male, right? 24-year-old males. What is the probability that a randomly selected murder victim in 2005 was a male, given that the victim is 20 to 24 years old? Okay, all right, so it's pretty messy. You gotta like read through it and decipher what all these percentages are, what they mean. So 19.1% of all murder victims were between the ages of 20 to 24 years old. Okay, so the probability that we have a murder victim that's between the ages of 20 to 24 years old in that year were 0.191, right? 19.1%. In 2005, 19.1% of all murder victims were between the ages of 20 to 24 years old. Also in 2005, 16.6% of all murder victims were 20 to 24-year-old males. So the probability that someone is 20 to 24 years old and male, that's equal to 0.166. What is the probability that a randomly selected murder victim in 2005 was male, given that the victim was 20 to 24 years old? So find the probability that this person is male, given that they were 20 to 24 years old. That's what we want to know. Good. So if you know what this means, interpret what this means. If you're listening to a police scanner and you're just listening to things, and the police announce that they have found a murder victim, okay, and you have to think to yourself, what's the probability that this murdered victim is a male, right? So you're kind of thinking to yourself what that is. Now this exercise did not tell us what that answer is, so we don't know. Probability that you're a male and you're a murder victim, we don't know. But whatever that is, okay? And now, over the same radio, they spit out some additional information. Now you know, okay, it's not just that it's a male. We also know that this, we don't know that it's a male. We want to know what's the probability that it's a male, right? It could be a male, it could be a female, I don't know, we don't know. But then we do have some information. They kind of spit out some information here, given that they found out that this person, male or female, is between the ages of 20 to 24. Okay, so now we want to know what's the probability that it's a male, given that we know their age is between 20 to 24 years old. According to our formula, this is equal to the probability of being male and between the ages of 20 to 24 divided by the probability that you're between the ages of 20 to 24. Right? That's the formula we have. And so the probability that you're male given, that you're between the ages of 20, the male given that the victim is between 20 and 24 years old is equal to 0.166 divided by 0.191. Okay, so take those two numbers and divide them. 0.166 divided by 0.191, and we get 8691. 0.8691. Right? Very, very high. So if you hear information over a police scanner and they go, there's a dead body, and you're thinking to yourself, I wonder if this dead body is a male or female. What are the odds it's a male or female? And then they go, okay, we got some extra information. We know that this dead body is somewhere between the ages of 20 to 24. Now we are 86.91% confident that the body must be that of a male, right? So clearly a lot more males in this age range die of murder than females, right? There's the complement must be true, right? If not a male, there must be a female. That must mean that the probability that it's a female, given that the body is a victim of between the ages of 20 and 24, must be the complement, 1 minus the probability that it's a male, given that it's a body between 20 and 24 years old. So this must be 1 minus 0.8691, right? The rest of it, which adds up to 0.1309. Why am I having, I need to get more coffee. Yeah, very nice. So there's only a 13% chance that it's a female, given that we know that the body is between 20 and 24 years old. Any questions? No? 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 Okay, moving on. Okay, so here's what the author did. Same thing. Probability that it's a male, given that they're between 20 and 24 years old, is equal to the probability that they're male and 20 and 24 years old, divided by the probability that they're between 20 and 24 years old. So we get the same answer. And then here comes this multiplication rule. Now, I kind of hinted at this already in that ping pong example. Remember that our, I don't like that they presented it to you like it's a brand new thing. All we're doing is that we're still playing with this exact same conditional probability, right? The probability of F given E, we just said is equal to the probability of F and E divided by the probability of E. So now if we multiply both sides by P of E, multiply this side by P of E, then this cancels, that cancels, and what I'm left with is this multiplication, probability of E times the probability of F given E is equal to the probability of F and E. So now I'm just going to flip it around, kind of a hinge here with the equal sign, flip it around, and I'll write that the probability of F and E is equal to the probability of E times the probability of F given E, right? All I did is I flipped these around, or I read it this way. Probability of E and F is equal to the probability of E times the probability of F given E. And then one last thing, the order matters, right? Order matters here, inside here. The order does definitely matter. But inside here, this order does not matter. With the AND statement, I'm allowed to move these around. So just for the sake of making it pretty, I'm just going to move those around and say that this is the probability of E and F. Right? It makes sense that the order shouldn't matter. If we go back to our little ping pong ball example, I wager event E, and then my friend wagers stuff on event F. The probability that we both win, well, it doesn't matter if he wins first and I win second. It doesn't matter, or if he wins second, I win first. It doesn't matter. It's just we're looking for the probability that we both win, right? The probability that both events happen. This is this probability of E times the probability of F given E. Good. Good. Okay, now on the other hand, if we had the other order, if we had the probability of E given F, then this is equal to the probability of E and F divided by the probability of F. Again, we could multiply both sides by the probability of F, multiply this side by the probability of F. These guys cancel. And so you end up with the probability of F times the probability of E given F, which is equal to the probability of E and F. Again, if you just think of this as a little hinge and flip these around, kind of flip them around, or read it this way. I just want to put this first equals this. So I'm just going to flip it around and rewrite it as the probability of E and F is equal to the probability of F times the probability of E given F. Good. Okay, so this probability, this, is the exact same one as this one, but there's two ways to express it. The probability of E and F is equal to the probability of E times the probability of F given E, right? That's one way to do it. Or this one, the probability of E and F is equal to the probability of F times the probability of E given F, right? So there's two ways to say the same, find the same probability of E and F. We just have to be careful because the order is very important here. The conditional probability really cares about the order. So we'll see some examples where you get to figure out the same. It's important to know both ways of figuring out the probability of E and F because there's a very specific way to find it in a particular problem. Okay, so anyway, going back to this, that's what they're presenting to you here. The probability of E and F is equal to the probability of E times the probability of F given E. And what we just discovered here, let's zoom in, is that if we want to, we can also introduce another way of stating this. This is also equal to the probability of F times the probability of E given F. Right? So this and this product both give you the same answer. Good, maybe, sort of, kind of. Okay, let's go back to another example involving the murder victims. So in 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 86.5% of murder victims were male, given that the victim was between 20 and 24 years old. What is the probability that a randomly selected victim in 2005 was between the ages of 20 and 24 years old? Male. Okay, so the probability that they were 20 to 24 years old and male is equal to the probability that they were 20 to 24 years old times the probability that they were male given that they were 20 to 24 years old. Good. So I have an AND statement here. Now these get really messy here, but I have an AND statement. That's what they want to know. What is the probability that a randomly selected murder victim in 2005 was 20, 24 years old and male? Right? That's what they want me to find out. So according to my property, this is kind of like the what did they use, E and F? This is like E and this is F. The probability of E and F is equal to the probability of E, probability of E and F. It's getting really messy. Erase. So I'll put it over here. Probability of E and F, right? This is the E, event E is that they're 20 to 24 years old. Probability and F, and we're saying event F, we're using EF to represent male, right, is equal to the probability of E times the probability of F given E. Good. Okay, and did they give me that information? 19.1% of all murder victims were between the ages of 20 to 24 years old, right? So this is the 0.191 times this one. Okay, so also 86.9% of murder victims were male given that they were between 20 and 24 years old. That's this one, 0.869. So these are the two that I have to multiply to give me the answer I'm looking for. Good. Now, we know that this is also equivalent to the other way around. So this is also equivalent to the probability that they're male times the probability that they are between the ages of 20 to 24 years old, given that they're male. Right? But this particular word problem didn't give me that. So it's equal to that, but this word problem didn't give me the necessary probabilities to figure it out that way. Right? If they had given me the probability that a murder victim is male, if they had given me that, I could use it. If they had given me the probability that a murder victim is between the ages of 20 and 24, given that they're male, if they had given me this probability, I could use it. But if you read the word problem carefully, we see that these are the two that they gave me. So in this case, this is how I get it. So we multiply 0.191 times 0.869, and we get 1659.7. Moving it up, we're going to go to 1660. So this is going to be equal to 0.1660, or about 16.6% chance, right, that they're male. I'm sorry, that they're 20 to 24 and male. Okay. I do this so I can, because I'm lazy about copying everything, so this statement kind of stays across. Any questions? Right, so this is our answer. Questions, 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 questions? No, no, no. Okay, so this is what the author did. Same answer. No questions, no questions, no questions. Okay, things are getting a little confusing, right? Told you guys, probability is a very serious topic, very, very difficult, very, very challenging, requires a lot of time, a lot of effort, a lot of energy. So if you're struggling with it, that's normal. That's what's supposed to happen. So it requires hours and hours and hours upon hours and hours of studying and thinking and doing homework and studying to be able to start to get a good sense of what's happening. And if you don't devote that kind of commitment to it, if you don't make that kind of commitment to it, it's unlikely that you're going to get it. Okay, so if you only put in a couple of hours into this and you still don't get it, yeah, that makes sense. Okay, I'm expecting about 3 to 4 hours per section is, ballparking it of what I expect. might be a little longer, might be a little shorter, but I'm expecting about 3 or 4 hours per section in terms of reading the section and doing the homework. So we're already in 5.4. So, 12 to 16 hours worth of homework for these 4 sections seems reasonable to me. Now, when I say that, I don't mean, oh, you should sit down and spend 16 hours on it nonstop. It's just that total, cumulatively, it should take about 12 to 16 hours to complete the homeworks for these 4 sections. That won't always be the case throughout the entire semester. It's just that Chapter 5 probability is pretty tough, so it takes a lot of work. When we go back to Chapters 1, 2, and 3, you'll find that things are a little easier. Chapter 4 is also really hard and takes a long time. Chapter 6 is fairly easy. Chapter 7 is pretty easy. And then Chapters 8, 9, 10, and 11 are really hard. Harder than this chapter, I think. So they take a really, really long time. So I say that so that you can prepare yourself to give carve out the time that's needed for you to be successful in this class, and make sure that you don't take on too many units this semester. Right? You're still in time to adjust your schedule, and I think very often people take on too much, especially now that we're doing so many things over the internet, online classes. It feels like it would be easy to take on a bunch of units, take on a bunch of classes, because it's easier to squeeze them into your schedule and all that, and that's fine. There's a lot of flexibility there, so that's really good. But at the same time, there's a lot of work that needs to get done. So consider your work schedule, consider your family responsibilities that you might have, the other units that you're taking on. Think about whether you're someone that normally does really well with math, and so you're kind of head of the class normally, or you're someone that just kind of struggles with math, and you're going to need a little extra time. So consider all those things as you kind of decide to adjust your schedule. I think you have until the end of this week to figure out whether or not you want to stay in this class, or if you'd like to withdraw from this or any of your other classes. The actual date is on the syllabus, and I believe there's also an email out there that lets you know when that is. Okay, so everyone should hopefully by now already open an account on MyStatLab. I recommend that everybody open a free 2-week trial account. That way you can just get started right away, whether you have the money or not. And I know that some of you might not be totally committed to taking this class this semester yet, so this gives you a little bit of an opportunity, a little bit of window to decide whether or not you want to keep it. So open that free account, go over to the video that has the registration process for information on how to do that, and get started on this homework so that you can get a better sense of what's expected of you this semester, and again, be able to judge whether or not you have the time to be able to do this. Okay. Any questions or comments on anything?
I have a quick question.
Yeah.
We're still on track with the time frame of how homework's due and how the test for Chapter 5 is still on?
No. Yes and no. So if you go on to the account, you'll see that there's a due date associated there. I have to put a due date when I created the assignment, when I assigned it to you. So in order to make it available for everybody, so your entire homework for the entire semester was available on day 1, but I had to pick dates. So I just kind of arbitrarily picked some dates kind of sprinkled throughout the semester, but those dates are pretty fluid. So I would never change the date to make it sooner. I wouldn't surprise you and say, oh, well, it used to say the end of the month, but now it's due tomorrow. I wouldn't do that. So the date that's on there wouldn't roll closer, but it might roll farther. So as we move through the semester, as we go through the different sections, I will definitely kind of adjust where we are, depending on how slow or fast we're going. My answer would be, kind of pay attention to those due dates that are on there, and they can and will, periodically kind of be adjusted. So I know that right now there's some stuff that's being due. I think that sections 1 and 2 are probably going to stay the same. I think people have had enough time to get those 2 sections done by the stated due date. But sections 3 and 4 and moving forward, I'll probably space them out to give people a few extra days from the date that's on there. Okay, so just kind of pay attention to that guy, and if it doesn't hurt to ask if something should be changed, and I might consider it and move the due date so that people can have a little extra time. Having said all that, though, remember that you can always work on it past the due date. It's just that if you work on it past the due date, there will be a little penalty. I think it's 25% of any of the individual exercises that you do past the due date on any assignment.
Okay, thank you.
Sure. Any other questions? No? Okay, this stuff gets really, really, really tricky, so please read the book very carefully, every page. Don't just skim it. You got to read the book, you got to read the definitions, you got to look through the examples that the book gave you, watch these videos, hopefully they're helpful, and attempt the homework. The homework has a bunch of help me solve things, right? So those are good, but don't overly rely on them. Try not to overly rely on them. If you didn't know how to answer something and you had to use the help me solve this to get the answer, that's fine, but you still haven't answered it, right? So put down the correct answer, that's fine. You use the help me solve this, that's fine. You can always come back to it later. Wait till the next day. Come back and read the question one more time and see if now you're able to do it on your own without any assistance, right? Because that's what you'll need to do when the test comes around. Those help me solve these options are not going to be there when the test comes around. So make sure that you can do these questions without any assistance at some point. Good? Questions, comments, issues? No.
So I guess I just want to piggyback off of what she was saying earlier about the chapter sections.
Yes.
So since they're all due tomorrow, are we going to be penalized if we don't complete chapter, for example, from 4 to 5 and 6, including the quiz?
So like I said, I think 1 and 2, sections 1 and 2 are going to stay the same. I think that's fair. People have been given enough time to work on them. Sections 3, 4, and moving forward will be changed.
Okay, thank you.
Any other questions? No? Okay, that's a good place to stop. Have a great weekend, full of stats, full of math, and I will see you on Monday.
Monday's a holiday.
Oh, okay.
Are we having class?
No, we're not. So I will see you on Tuesday.
Yay.
All right. Have a good weekend.
Have a good weekend, everyone.
Okay, bye.
Bye.